For centuries, our world has been built on a simple idea. It is the language of on and off, of 1 and 0. We call these bits. Every email you send, every photo you take, every movie you stream, it is all just a long, long string of these ones and zeros. Classical computers, from the giant mainframes of the past to the smartphone in your pocket, speak this binary language. They are incredibly powerful, able to perform billions of calculations every second. But even these amazing machines have their limits. Some problems are so complex with so many possible answers that even the fastest supercomputer would need thousands of years to solve them. What if there was a different way to compute? Imagine a computer that doesn't have to choose between 1 and 0. Imagine it can be both at the same time. This is the strange and wonderful world of quantum computing. Instead of bits, these machines use qubits. A qubit can be a 1, a 0, or a blend of both simultaneously. This mind-bending property is called superposition. Think of a spinning coin. While it's in the air, it's neither heads nor tails. It is a mixture of both possibilities. Only when it lands does it settle on one state. A qubit is like that spinning coin, holding multiple values at once, allowing it to explore a vast landscape of possibilities, all at the same time. But the magic doesn't stop there. Qubits have another mysterious ability called entanglement. Albert Einstein famously called it spooky action at a distance. When two qubits are entangled, they become linked in a profound way. No matter how far apart they are, across a room or across the galaxy, the state of one instantly affects the other. If you measure one qubit and find it is a 1, you will know in that very same instant that its entangled partner is a 0. This cosmic connection allows quantum computers to weave together information in ways that classical computers simply cannot, creating an exponential increase in processing power. This quantum partnership of superposition and entanglement is the key to their incredible potential. A classical computer with 3 bits can only represent one of 8 possible combinations at any given moment, like 001 or 110. But a quantum computer with 3 qubits can represent all 8 combinations simultaneously. As you add more qubits, the power grows exponentially. With just a few hundred entangled qubits, a quantum computer could hold more information than there are atoms in the known universe. It's a fundamentally new way of processing reality, one that mirrors the strange rules of the quantum realm itself. For a long time, building a powerful quantum computer was just a dream, a concept on a blackboard. But in October 2019, something remarkable happened. Scientists at Google announced they had achieved a milestone called quantum supremacy. They built a quantum processor named Sycamore that performed a specific, complex calculation in just 200 seconds. Why was this so important? Because they estimated that the world's most powerful classical supercomputer at the time would have needed about 10,000 years to complete the same task. It was a hello world moment for a new era of computation, a demonstration that these machines were not just theoretical. This event was like the first flight of the Wright brothers at Kitty Hawk. It wasn't a commercial airliner and it didn't travel very far, but it proved that powered flight was possible. Google's achievement did the same for quantum computing. It showed that, with enough ingenuity, we could build devices that operate on the laws of quantum mechanics to solve problems beyond the reach of our best classical machines. This sparked a global race, with companies and research institutions around the world pouring resources into building bigger, better, and more stable quantum computers. The journey had truly begun. So what does one of these groundbreaking machines actually look like? Forget your standard desktop tower or sleek laptop. A quantum computer often looks more like an elaborate, futuristic chandelier. It is a stunning cascade of gold-plated wiring, pipes, and cylindrical chambers, all housed within a large, protective metal shell. This intricate design is not just for show. Every single component is part of a sophisticated system designed to do one thing: protect the incredibly fragile qubits at its core from any outside interference. The slightest vibration or a stray magnetic field can disrupt their delicate quantum state. The most critical part of this protection is an extreme cooling system. To maintain their quantum properties, qubits must be kept incredibly cold, at temperatures colder than deep space. We're talking about just a fraction of a degree above absolute zero, the coldest temperature possible in the universe. This is why the heart of a quantum computer is a massive refrigeration unit called a dilution refrigerator. This device uses a complex process to chill the quantum chip, creating a pristine, ultra-cold and stable environment where the strange dance of superposition and entanglement can take place without being disturbed by the noisy, warm world outside. Why go to all this trouble to build such a complex and cold machine? The answer lies in the types of problems quantum computers could help us solve. Think about creating new medicines. Designing a new drug involves understanding how complex molecules will interact with each other inside our bodies. This is an incredibly difficult simulation for classical computers because there are countless possible interactions. A quantum computer, however, could simulate these molecular behaviors directly, exploring all the possibilities at once. This could dramatically speed up the discovery of new life-saving drugs and personalized treatments for diseases that are currently incurable. Another huge area is artificial intelligence. AI and machine learning are already changing our world, but they are hungry for data and processing power. A quantum computer could analyze enormous and complex datasets in a fraction of the time, finding patterns that are invisible to classical algorithms. This could lead to massive breakthroughs in everything from creating more advanced self-driving cars to developing AI that can understand human language and emotion with far greater nuance. It's like giving our quest for intelligence a supercharged new brain, capable of thinking in ways we've only just begun to imagine. The power of quantum computing also presents a new challenge for cybersecurity. The very same abilities that let them solve complex problems could also allow them to break the encryption methods we currently use to protect our bank accounts, government secrets, and private messages. This sounds scary, but the quantum world offers a solution as well. The same principles of quantum mechanics can be used to create new forms of quantum cryptography. This would allow for the creation of communication channels that are, by the laws of physics, completely unhackable, securing our digital world for the future. Beyond these fields, the applications are almost limitless. Quantum computers could help us design new materials with incredible properties like room temperature superconductors that could lead to perfectly efficient energy grids. They could optimize global logistics, finding the most efficient routes for shipping and transportation to save fuel and reduce our environmental impact. They could even create far more accurate climate models and weather forecasts by processing vast amounts of atmospheric data. In essence, quantum computers offer us a key to unlock a new level of understanding and control over the complex systems that shape our world. Despite the incredible promise, we must remember that we are still at the very beginning of this quantum journey. The technology is in its infancy, and scientists face significant challenges. The qubits themselves are incredibly fragile. The slightest disturbance from their environment, a tiny change in temperature, a stray bit of radiation, or a small vibration, can cause them to lose their quantum state in a process called decoherence. This leads to errors in the calculation. Researchers are working tirelessly to create better error correction techniques and build more robust, stable qubits that can hold their information for longer. Another major hurdle is scalability. While Google's Sycamore processor had 53 qubits, the truly world-changing applications will likely require machines with thousands or even millions of stable and interconnected qubits. Building and controlling such a large-scale quantum computer is an immense engineering challenge. It's like learning to conduct a symphony orchestra where every musician is a spinning coin that could stop spinning at any moment. Getting all those qubits to work together in perfect harmony, without errors, is the central task for the next generation of quantum physicists and engineers. It will likely be many years, perhaps decades, before you have a quantum computer in your home or on your desk. For the foreseeable future, these will be specialized machines used by scientists and large corporations to tackle very specific, very hard problems. They won't replace your laptop for checking emails or browsing the web. Instead, they will work alongside classical computers, taking on the tasks that are simply impossible for them. Think of it as a new, powerful tool in our scientific toolbox, one designed for exploring the frontiers of knowledge, and yet, the future is incredibly bright. Every great technological revolution began with small, uncertain steps. From the first steam engine to the first transistor, these inventions took time to mature, but they ultimately reshaped our civilization in ways their inventors could barely have predicted. Quantum computing holds that same potential. It offers us a chance to solve some of humanity's most pressing problems and to understand the universe on its most fundamental level. We stand at the dawn of a new computational age, looking out at a horizon filled with unimaginable possibilities.